Basic impulse insulation level, or BIL, is defined as the peak voltage that a transformer can withstand without failing due to an electrical surge. Therefore, a higher BIL indicates that the transformer is more resistant to surges. These surges can be caused by lightning strikes, utility switching operations, or other events that send a sudden burst of voltage through the power system. In the specified scenario, the transformer is initially designed with a BIL of 75 kV, which means that it should be able to withstand a voltage surge of up to 75,000 volts without experiencing insulation breakdown. The supplier's proposal to lower the BIL to 60 kV implies that the transformer would be less resistant to these high voltage surges. The impact of lowering the BIL on the performance and lifespan of the transformer is that it becomes more susceptible to failure due to voltage surges. This could lead to a variety of consequences, ranging from a temporary power outage to permanent damage to the transformer itself, necessitating costly repairs or replacement. The insulation within a transformer is designed to prevent the flow of current between conductors at different voltage levels. When a voltage surge exceeds the BIL, it can cause the insulation to break down, leading to a short circuit or other types of failure. The reason why the supplier might propose lowering the BIL is primarily economic. Manufacturing a transformer with a lower BIL typically requires less insulation material and less stringent manufacturing processes, both of which translate into lower production costs. However, it is crucial to carefully evaluate the potential cost savings against the increased risk of failure and the associated consequences. When deciding whether to accept a lower BIL, several factors should be considered. Firstly, the specific application of the transformer needs to be assessed. For example, is it located in an area that is prone to frequent lightning strikes or other sources of voltage surges? Secondly, the importance of uninterrupted power supply should be taken into account. Is the transformer serving a critical load where even a brief outage could have significant consequences? Thirdly, the potential cost of failure should be considered, including the cost of repairs, replacement, and any downtime that may result. If there are concerns about the reliability of the transformer, it may be prudent to specify a higher BIL. This will provide a greater margin of safety and reduce the likelihood of failure due to voltage surges. A higher BIL rating inherently provides a more robust insulation system capable of withstanding greater electrical stresses. The decision to accept a lower BIL should be based on a thorough evaluation of the risks and benefits, taking into account the specific requirements of the application. Remember that while the initial costs may be lower, the long-term costs associated with potential failures can far outweigh any savings. In addition to the basic impulse insulation level, there are other voltage ratings associated with transformers. These include the operating voltage, which is the normal voltage at which the transformer is designed to operate, and the test voltage, which is the voltage that the transformer is subjected to during factory testing to verify its insulation strength. The BIL is specifically related to the transformer's ability to withstand short-duration high-voltage surges, whereas the operating and test voltages are related to its performance under normal operating conditions. When evaluating the suitability of a transformer for a particular application, all of these voltage ratings should be considered. The standards organizations such as the Institute of Electrical and Electronics Engineers or IEE and the National Electrical Manufacturers Association or NEMA provide detailed guidelines and specifications for transformer design and testing, including BIL requirements. These standards can be used to ensure that the transformer meets the necessary performance and safety requirements. Furthermore, it is essential to consider the grounding system associated with the transformer. A properly designed grounding system can help to mitigate the effects of voltage surges and reduce the risk of insulation breakdown. The grounding system should be designed to provide a low impedance path for fault currents to flow back to the source, thereby minimizing the voltage rise during a surge. Also, surge arresters can be installed to protect the transformer from voltage surges. Surge arresters are devices that are designed to divert excess voltage to ground, thereby preventing it from reaching the transformer. Surge arresters should be selected based on the specific voltage levels and surge currents expected in the system. Ultimately, the choice of BIL and other protective measures should be based on a comprehensive assessment of the risks and benefits, taking into account the specific requirements of the application and the recommendations of relevant standards and guidelines. The supplier may be suggesting the lower BIL to reduce costs. It's vital to understand the ramifications of this change. Firstly, let's reiterate what BIL means. It's a measure of the transformer's ability to withstand high voltage surges without insulation failure. A higher BIL translates to greater protection against lightning strikes, switching surges, and other transient overvoltages. Secondly, consider the environment where the transformer will be installed. Is it in an area prone to lightning? Are there other electrical equipment nearby that could generate switching surges? These factors will influence the required BIL. Thirdly, what is the criticality of the load being served by the transformer? If a power outage would have significant financial or operational consequences, then a higher BIL is warranted. Fourthly, ask the supplier for the technical justification for the lower BIL. What data supports their claim that a 60 kV BIL is sufficient? Ask for a detailed risk assessment that considers the factors mentioned above. Fifthly, consult with a qualified electrical engineer to review the supplier's proposal and assess the risks. An independent expert can provide an objective opinion and help you make an informed decision. Sixthly, remember that the BIL is just one aspect of transformer design. Consider other factors such as the transformer's impedance, cooling system, and overload capacity. Seventhly, document your decision-making process. Keep records of all communications with the supplier, the risk assessment performed, and the rationale for your final decision. This will be helpful in case of future issues or audits. Eighthly, consider the long-term costs. While a lower BIL may save money upfront, the cost of a transformer failure can be substantial. Factor in the cost of replacement, downtime, and potential damage to other equipment. Ninthly, explore alternative solutions. Perhaps there are other ways to reduce the cost of the transformer without compromising its reliability. For example, could you use a different type of insulation or a different cooling system? Tenthly, remember to comply with all applicable codes and standards. The National Electrical Code or NEC and other relevant standards may specify minimum BIL requirements for certain applications. The decision to reduce the BIL of a transformer should not be taken lightly. It requires careful consideration of the risks and benefits, as well as consultation with qualified experts. In most cases, it's best to err on the side of caution and specify a higher BIL to ensure the long-term reliability of the transformer. Also consider the type of insulation used in the transformer. Different types of insulation have different dielectric strengths, which affect the transformer's ability to withstand voltage surges. Common insulation materials include mineral oil, cellulose, and synthetic esters. Mineral oil is the most widely used insulation material in transformers. It has good dielectric strength and cooling properties, and it is relatively inexpensive. Cellulose insulation, typically in the form of paper or pressboard, is also commonly used in transformers. It has good dielectric strength and is biodegradable, but it is more susceptible to moisture than mineral oil. Synthetic esters are a newer type of insulation material that offers several advantages over mineral oil and cellulose. They have high dielectric strength, better fire resistance, and are more environmentally friendly. The type of insulation used in a transformer can affect its BIL rating. Transformers with synthetic ester insulation typically have higher BIL ratings than transformers with mineral oil or cellulose insulation. Also consider the design of the transformer's windings. The windings are the conductors that carry current through the transformer. The design of the windings can affect the transformer's BIL rating. Transformers with interleaved windings, for example, typically have higher BIL ratings than transformers with non-interleaved windings. Interleaved windings help to distribute the voltage stress more evenly throughout the winding, reducing the risk of insulation breakdown. In addition, the spacing between the windings and the core can affect the transformer's BIL rating. Transformers with greater spacing between the windings and the core typically have higher BIL ratings. This is because the greater spacing reduces the electric field stress on the insulation. Consider the transformer's tap changer. A tap changer is a device that allows the transformer's turns ratio to be adjusted, which changes the output voltage. Tap changer can also affect the transformer's BIL rating. Transformers with unload tap changers, for example, typically have lower BIL ratings than transformers with offload tap changers. This is because unload tap changers introduce additional insulation stresses into the transformer. Also consider the transformer's cooling system. The cooling system is responsible for removing heat from the transformer. The type of cooling system can affect the transformer's BIL rating. Transformers with forced air cooling, for example, typically have higher BIL ratings than transformers with natural air cooling. This is because forced air cooling provides better heat dissipation, which reduces the risk of insulation breakdown. The age of the transformer is also a factor. Over time, the insulation in a transformer can degrade due to thermal stress, electrical stress, and contamination. This degradation can reduce the transformer's BIL rating. It is important to periodically test the transformer's insulation to ensure that it is still within acceptable limits. Insulation testing can be performed using a variety of methods, such as megameter testing, power factor testing, and frequency response analysis. These tests can help to identify insulation weaknesses before they lead to a failure. The location of the transformer is also something to think about. Transformers that are located in areas with high levels of pollution or humidity are more susceptible to insulation degradation. This is because pollutants and moisture can contaminate the insulation, reducing its dielectric strength. Transformers that are located in coastal areas are particularly vulnerable to salt contamination, which can significantly accelerate insulation degradation. Also consider any previous repairs or modifications that have been made to the transformer. If the transformer has been previously repaired or modified, it is important to ensure that the repairs or modifications were performed correctly and that they have not compromised the transformer's BIL rating. For example, if the transformer has been rewound, it is important to ensure that the new windings have the same BIL rating as the original windings. The decision to accept a lower BIL should be based on a comprehensive risk assessment that considers all of these factors.